Okay, good morning, everyone. How did the homework go, as usual? Do you have any questions about it? Okay. 49. Oh, good. Okay, we do 49. Actually, whether you've asked or not, I was definitely planning on doing that. So let's look at number 49. And they're giving us the graph of a function, and we have to see how the derivative looks like. So I will reproduce the graph. And the graph seems to go like this and like that. All right, so that's our graph, that's the function f. And the question is to sketch the graph of the derivative. Okay, so let us study a little bit the derivative. How does it work? So there is no very clear guidelines in the term. The derivative doesn't seem basically, let me copy it. Yeah, so doesn't seem to have this peak like this. There is nothing clear about it. So let's see how it's gonna work. So we will follow the tangent line, and then we see what's happening. Okay, these are the tangent line, and that's what we're gonna see. So how are the tangent line? Positive, 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 positive across the board. They are really all the time positive. But let's see how, again, study them a little bit more. They are positive, but they seem to be getting less positive. So they are positive, but they are really getting less and less positive. So if I'm gonna describe the derivative, the graph right down here. Okay, let me here sketch the graph. Okay, I'm gonna sketch the graph down here. So how does it look like? It's positive. So when x is negative, this is taking positive values, but those values are getting less and less. So those values, wherever they start, they are getting less and less and less and less and less and less. So they are getting less and less, right? And then what's really doing after that? At some point here, at some point right here, they are changing from being more positive, so being less, to being more positive. So what's the graph is going to do at some point? What do you think the graph is going to do? So the slopes are getting positive, but less and less and less. So they are decreasing in value. They are decreasing in value. At some point, what they start doing? They are still positive, but they start increasing in value. So how is going to happen? So it's going to basically bottom up and then start increasing in value. And that's really how f prime is going to look like. Right? So in terms of the function, what's the function is doing? Basically, at the beginning, the function is changing, but it's changing less and less and less. So what do I mean by changing less? Watch carefully. If I take 1 unit here, that's how much the function increase. If I take the same amount of change in x, it's increasing less. The function increases less. So that's really, the derivative is really reflecting the fact that the function is increasing, but less and less and less. And then at some point, the function start increase, but faster and faster and faster. And the derivative is gonna go like this. Right? So let me take another question problem. I would like to do also number 50. Those are nice problems. And I will put the graph, I don't know if I assigned it, but I will put the graph in front of you. And I want you to think through it a little bit, and then we discuss it. So the graph looks like this. It goes like that. And then it kind of wiggle and go like this. No corners, nothing or whatsoever. That's how the graph looks like. And that's the graph of the function itself. Okay. And down here, we're gonna sketch together the graph of f prime. So I want you guys to, a little bit in front of you, see how do you think the graph of f prime is gonna look like. And then we're gonna discuss it the best possible way. So I mean, as before, we don't have like a peak where we know exactly that it's 0. So it's a little bit harder than the one we did yesterday, but we should be able to handle it. So I give you 2 minutes to interact with it, and then I will try to ask you questions to see what's really going on. Okay, anybody would like to tell me a little bit, just in mute, and tell me a little bit, how do you think the graph should look like? So where do you want me to start? In this quadrant. So in the quadrant 1, 2, 3, or 4. You just put on chat which quadrant you want me to start. Wyatt, tell me quadrant 2. Because is he correct? So if I am right here, because he's right, because the derivative are positive. So definitely quadrant 2. So that's question number 2. And how is the derivative going to be? Is it like increasing? Chris tells me quadrant 3. Why quadrant 3? If I draw it in quadrant 3, it means I'm telling you the values are negative. Okay, so if I put, let us say this is -1. Okay, and if at -1 I am right here, it means you're telling me that the derivative is negative. It means you're telling us that the slope here is negative. But is the slope negative or positive here? It is absolutely positive. So at -1, so I'm focusing only on one point, my derivative is up here because the values are positive, they are not negative. Okay, so we're not gonna confuse f from f prime. F prime is basically, it's the slope. For us to be able to draw those, we have to only to see it as a slope. So right here, the slope is positive. It means the value is gonna be in the second quadrant, not the third, okay? So now question number 2, so very good. And where do you want me to start? Do you think I should start up here or here? Here or here? Where do you want me to start? A or B? And then we're gonna say why. B, Elisa, everybody tell me B, and why it is B, because what's really doing? If you think a little bit about it, the way the graph is, the tangent here is almost 0, because the graph is kind of flat and a little bit flat. So if I draw the tangent, it's very, very much, not zero, but it's very small because the slope here is very small. So when I'm gonna graph this, okay, so I'm gonna graph this, I'm gonna start here because the function itself is flat, almost. It means it does not changing much. Remember, the slope, I'm computing the change of output over change in input. If the function is almost constant, there is no much change in the output. So it's fairly small. And then it seems to getting larger. So I'm following now my slope, getting larger, larger, up to 0 is getting larger. And then what's doing here? At some point here, so it keeps going larger. At some point, but we, as I said, we're going to give this a name, the slope change. So how is this going to affect us? I mean, how can I reflect this here? How I'm going to reflect that? So the slope is changing. So it's growing. And then what's doing after that? At this point, what do you think the slope is doing? First, is it positive or negative? This first simple question. Positive or negative? Positive. And then what's really doing after that? Is it keep going increasing? Is it keep going larger or getting smaller? Okay, it's heading back to 0 because the function is actually, as you realize, the function is really flattening. It means when I compute the slope here, it's really going to be very small. So it's kind of peaking and then heading towards 0, always positive, always positive. That's crucial. It's never getting negative because to get negative, the function has to go down. And the function doesn't seem to be going down. The function seems to be flattening. It's like approaching an asymptote in a way. So the function is actually kind of flattening. And so this is the graph of the derivative. Okay, so we're following those slopes very, very carefully. And the slopes are positive and they are getting larger and larger till some point, and then they are getting less and less. So the function is basically increasing very fast at the beginning. It's increasing fast, and then at some point, the function starts changing, but it's less and less. So the rate of change intuitively is becoming less and less and less, and it's heading towards 0. This point where the things change, we will be calling it a name, and we will be calling it eventually inflection point. So this point is an important point. We'll be giving it a name, and it's called the inflection point, but don't worry about it right now. Okay, all right, so this takes care of 2 problems. Any other questions before we proceed? It's your chance to ask any question you want. All right. Okay, so we move on. So we absolutely move on. We're gonna talk a little bit about notation for the derivative, and then we move to section 3.3. So notation for the derivative. Notation. Okay, so we already know a notation. It's not like we don't. So we already know a notation, but there are other notation which is crucial. So let us, and they are based on the meaning of the derivative. So suppose y is a function of x. Okay, and let us see what does the derivative mean, f prime of x. Let us see what the definition is. It's, we take, so this is the picture always, never leave us. What do? We take a point x and we move a little bit from it, a little bit, that's really my h. And then we take a point here and we compute how much y change, f of x plus h minus f of x, and then we divide this by how much x change. And then we let x, the change, become close to 0. So what we do, basically, we take this change of y over the change in x. So if I call this delta y, the change in y, and I call this a change in x, then this is going to be the following. The limit of. And that's to motivate the definition. It's basically what I am doing is I start with X, I move tiny bit away from it, and ask myself, how much did Y change when I did a little bit, when I moved a little bit, over the change in X. And then we let the change in X go to 0. Because H and delta X are exactly the same. So that's really what we're doing. So the change over the change, and then we let the change becomes very, very small. And this will motivate the following notation for the derivative. So, and this is motivate the following. Another way to write the derivative. This will motivate the following. F prime of X, and that's now, it's a notation, is another notation for it is dy dx. So dy by itself doesn't make any sense. Dx by itself doesn't make any sense. What makes sense is the ratio dy dx reflect. The nice thing about this notation, it actually tells us intuitively what we're doing. It tells us that you're taking change of y over the change in x, but it's the limit when the change in x becomes very small. And we usually call this Leibniz notation. So that's a mathematician who actually came up with this notation, and it's called Leibniz notation. And it's crucial because it really tells us what I'm doing. I'm taking the ratio between them. And sometimes we write it, and I will write it, or the book write it. Sometimes we write d dx, we drop a bracket, and then we put the function f inside. So all those notations mean the same thing. It means the slope of the tangent line in a graphical meaning. Now, if I'm emphasizing at a specific point, not the formula in general, if I'm emphasizing a specific point, and then the notation would become dy dx, and we put like a line slash at x equal to a. So we change a little bit the notation, slash x equal to a. So if I am emphasizing a point, then I put dy dx x equal to a. Extremely important notation, very much so. And at some point, people will use this notation even more than that, because it really tells me that x is the name of my variable, and I'm finding the change of y over the change in x. And sometimes, of course, I will also write y prime. So all those notation mean the same. Now, let us say in the case, suppose that we're working with the position function. So suppose s of t is the position function. It means you have an object which is moving, and s tells you where the object is as a function of time. So that's what s is. So in this case, what will be a good notation for the derivative? And in this case, the derivative, let us remember, is what the derivative is. But in this case, the derivative has a very specific meaning. And what's the derivative in this case? What's the derivative in this case? Back to you. What's the interpretation of the derivative if s is the position function? Do you forget this by now? Anyone? No, doesn't have to be.
Velocity.
The velocity, absolutely. It's how fast, crucial. It's how fast the object is moving. So if I take the top is the distance traveled, or the change in position over the time h divided by time, that's velocity, crucial. The derivative of the position is the velocity, is how much traveled over how long, over a very short period of time. Okay, and we have a notation, sometimes you write in v of t, mention the velocity. Okay, so let us remember always, if the function doesn't have to be quadratic, the s of t could be anything under the sun, it's just a position. It's quadratic in the problem we took because we always took the idea of a stone, which is go up and go down. In this case, physics tells us that it is quadratic, but it doesn't have to be quadratic at all. So suppose S is a position function. So S prime is the velocity. So that's the velocity. It's the derivative of the position. And now what is the notation that it's really what's the notation that's parallel to the one before it? In this case, we're gonna write the following. The t, time, is my input. So this has to be dt, there is no dx in here. And up here, it should be ds, because it's the change of position over change in time. So velocity or the derivative, that's the notation we use for it, okay? And then it's a very important notation, because this really tells me that what I am doing, I mean, in my mind, that's what I'm finding, how the velocity, how the distance is changing with time, how the distance is changing with time. Now, the dt really tells me what the name of my variable. So suppose I have y is, instead of using x, I use for the name of the variable q. Okay, I can use any name. So q is the name of the variable. And then f prime of q in this case is going to be dy, but this has to be dq. So we have to be very careful. It doesn't have to be x. This here tells me the name of my variable, whatever the name of my input is. X, that's x. Q is q. T is t. So we have to be careful with the notation. Okay, so a very straightforward example. I mean, we've worked with the derivative. Suppose s of t is, okay, I'll keep it here a little bit. So suppose s of t is not quadratic, is equal 30t. So it means an object is moving, okay? An object is moving, and at every moment in time, its position at time t is given by 30t, okay? So this is my object, and it's moving. So at t equal to 0, it's at 0, and every moment in time, okay, that's the graph. So it's not quadratic by any stretch of the imagination. Okay, so what is the velocity in this case? So what's the velocity? The velocity or the SDT. Okay, so what is the velocity in this case? Do we know? By now, do we know what the velocity is? The velocity is the derivative. Since this is a line, the derivative is nothing more than the slope. And it depends on the unit. We can introduce units, so whatever. Let us say feet per second. I'm just making up mine. And what does this really make sense? Does this really make sense have a constant velocity? Let's see. If this is a line, it means every unit of time, the velocity change. So if we start here, we move 1 unit. If the slope is 30, it means in 1 unit of time, the distance changed by 30. So it's a constant change. Another unit of time is changed by 30, the distance. So it's definitely, it makes sense to have a constant velocity because the object is moving by the same distance over the same period of time. So the velocity is constant. In this particular scenario, it's not quadratic, it's just a linear. So in this sense, having a constant velocity definitely makes sense because the object is moving by the same amount over the same amount of time. Okay, all right. Now we're moving to the part that since I've taught this class millions of times, that most of you are familiar with, because I know that not a lot of you, I know that a lot, not all of you, I know that a lot of you had calculus A, B, and BC or all this stuff. So now we're going to move to the part that usually the students are familiar with, but you guys will have to learn it all over. So section 3.3, rules of differentiation. So what do we mean by that? Okay, so what we did so far, we took a function, whatever, let us say f of x equal x squared, and we found its derivative. So in the first section, 3.1, we focus on one point, find the derivative at 2, or the slope of the tangent at 2, or the velocity at 2. In section 3.2, we moved a little bit and said, okay, instead of finding the derivative at a specific value, why don't you find a formula? And we did in general. So we found a formula, and you guys, you have problems around it. So we found a formula for it. And when we did that, we get 2x. That's the formula. Now, the benefit of a formula is that if I want f prime at 1, I don't have to do the same process again. It's 2 times 1. I want f prime at 50. I don't have to do the process again. I do 2 times 50, which is 100. Okay, so that's really what we started in 3.3. Now, in this section, some people, very smart people, gave us the formulas for most of the functions. So they told us what the formulas are, and our job is to learn them and to start applying them instead of having to do this tedious work every time. Even though you will have to do it, you will be tested on it, but it will avoid us doing this, all this work. So what are the rules? The first two are the one I've talked about yesterday because we can. So the first thing is that if a function is constant, it doesn't change. So this is my function. Then in this case, the derivative is equal to, quickly, all of you should know. Remember, you're finding the slope. The derivative is 0. So if a function doesn't change, when I'm computing the change in y over change in x, there is no change in y. The derivative is 0. The other case that I also talked about, if a function is linear. It means linear. Here, m and b are constant. Let's get that straight. M and b are constant. And then again, so that can go up, come down. In this case also, the derivative is basically the slope itself is equal to m. Okay, so these are the two cases that we considered yesterday. Now, of course, those are the simple case. What if my function is x squared, x cubed, x to the power 100, and so on and so forth. So the first rule is what we call the power rule. And this has to be memorized, no more, period. Power. Power rule tells me the following. Okay. Suppose that my function is f of x equal, that's my function, x to a certain power n, x squared, x cubed, x to the power a half. Then the derivative is the following. You take the power down, n times x to the power n minus 1. Okay, so that's a rule, there is a proof. So, or another way we can write this is the derivative with respect to x of x to the n. So immediately I want to introduce the gdx notation because of its importance, is equal to n times x to the n minus 1. Okay, so that's the power rule. Now the proof is actually what we've been doing. I mean, it's not really, it's an ingenious proof, but it's exactly what we did. So when people were finding this formula, it didn't really descend from anywhere. It's just, so if they want to find the formula, they actually did this computation. They did f of x plus h minus f of x over h. So to prove it, they actually did that. It's just we need the math we need, we don't have, we don't know. It's the limit as h goes to 0. That's really what's happening. If the function is x to the n, it means this is x plus h to the n. That's what they did. Minus x to the n over h. So that's what they compute. Now, I cannot go through the proof, but the idea is that there is a theorem, I don't know if some of you may know, called the binomial theorem, which helps them to expand, because they need to work with this limit. So they need to expand this. So there is a theorem in math called binomial theorem, which helps them to expand this quantity, because that's what we did. We expanded. When I had n to be 2, we expanded this, x squared plus h squared plus 2xh. So if you have 3, I need to expand it. So there is a theorem called the binomial theorem. that help us to expand this. After they expanded using the theorem, they were able to come up with this formula. So it's not really a magical formula, it's just a little bit of work. It's not really magical, but it requires a little bit of math background. All right, now our job is to know how to use it. So we're gonna take several examples where we will use it. So I will move and I will put this formula in front of us. So I will always refer to it. So the derivative of x to the n is equal to n x to the n minus 1. And now we're going to do several examples to elaborate this idea. So now the question is just find the derivative. It means nothing deeper in the first question. The derivative of each of the following function. All right. So I will do 3 and then I'll let you do yourself some and we check the answers. I start with, of course, the very basic one. So suppose f of x equal x squared, the very basic one. Okay, then what is f prime? So, and we have to use this formula verbatim. So according to this, my power is 2. That's n equal to 2. So this is going to be equal to power x to the power minus 1, which is 2x, which is, we know, we've done this like probably a million times by now. All right, so let us take another, again, straightforward example. X to the 5. So my n is 5 in here. My n is 5. So my f prime is my 5 x to the 5 minus 1. It means 5x4. Okay, so let us take some more. Suppose I take f of x equal 1 over x. Okay, so what shall we do here? We have to know the n. To be able to know the n, my function has to be written as x to the n. So the first step is going to be, we're going to rewrite. So that's crucial. So right now, we're going to rewrite as x to a power. So the only way I can use my formula if it's x to the power. So 1 over x is x to the power minus 1. And now, once I have it x to a power, I can use what I have. So my n here is negative 1. And then this is going to give me f prime equal minus 1 x to the minus 1 minus 1. It means minus x to the minus 2 or minus 1 over x squared. Okay, so the idea here is that if the function does not have the format x to the n, we have to rewrite it so it will have this format. So I'll give you now 3 more examples and then we move on. So suppose I have f of x equal cubic root of x. How am I supposed to find the derivative by using this formula? What should be my first step in the process? Math doesn't like cubic root, cannot function with them. So we have to, first we have to rewrite it. Crucial. Okay, cubic root of x, this x to which power? Quickly, a third. That's the first step. You cannot move forward without this. And now I have to apply the formula and then I take what my n is. My n here is a third. Okay, so my f prime is n, a third, x to the power, a third minus 1. It means it's a third x to the power. Now a third minus 1, if we do the math, minus 2/3, which is a third times 1 over x to the power 2/3. End of the problem. Okay, I will do one more. Suppose I give you f of x equal 1 over the square root of x. again, we have to rewrite it, x to a power. This will not be acceptable. I don't know how to deal with that. So I want you to rewrite it. Always we're rewriting now. Okay, and this will become x to which power? X to the power minus a half. Is that correct? Absolutely so. It's x to the minus a half because square root of x is x to the half. So now I use n is minus a half and then I proceed. We have to rewrite it. We cannot do that without this. So now my f prime will become my n x to the minus a half minus 1. And now these are fractions that I have to add. Minus a half minus 1 is minus 3/2. And that would leave me with minus 1 over 2x to the power 3/2. All right. So these are the basic function, power function, x squared, x cubed, square root of x. Those are the power function. And this is how we find the derivative. Okay. Now, let's do a little bit more rules. And then we have a nice, simple application to that. So the other rules are the following. How we usually build functions. Okay, what's the idea of building functions? When we build functions, the idea is that, okay, well, first we have the basic function, x squared, x cubed, x4. Then we create new functions from them by multiplying them by constant. So this is a new function obtained by stretching the other one. This is a new function obtained by stretching and reflecting. So that's how we build a new function from the basic function. And I can stretch by a factor of 5. So that's one way. So the question is, I know what's the derivative of x squared, for example. If I stretch it, if I multiply it by a constant, what will be the effect on the derivative of that? So that's really the second thing we're going to talk about. So this is state like that. If you have a function f, and you stretch it, so it means you multiply it by a certain constant c. So this is c here is a constant, absolute constant. So you change the function. Of course, you don't have the same slope. So if you take, like if any function of x and you stretch it by a factor of 2, you're gonna change the function. So the slope by itself is gonna also change. So c times f of x, what's the derivative? So the derivative of this new function, that's a totally new function, is actually simple. It's the constant c, you can take it out, you multiply it by the derivative of the function. Okay? Or using the d notation, it will become like this. The derivative with respect to x of c times f of x is c, so we can take the constant out, which is times the derivative with respect to f. Okay, so it's a c times the derivative. All right, so why this is helpful? Of course, because we have to work with all kinds of functions. So let us apply this rule very quickly. So how this rule will be applied. So question is, find the derivative of. Okay, and that's it. F of x equal 5x4. Okay, we're going to apply it verbatim. So this has the form, a constant, which is the 5, times the function. So it's the constant times the function. So what is the derivative? The derivative is the constant, I can remove it, times the derivative of x4. Okay, so it's the constant times the derivative. Now x4 is one of our basic functions. The derivative of x4 is 4, that's the n, times x to the 4 minus 1. It means it's 20x to the power 3. So you just basically get the constant out. Another example along the same line. Suppose f of x equal 2 over x squared. Okay, now actually let me change it to 4. 4 over x squared. Okay, and I need to find the derivative of this function. Okay, so how can I find the derivative? So that is the 4x, so we have to rewrite it as a constant times a function that I know how to find its derivative. So how can I rewrite this as a constant times a function? So we have to rewrite it to use our rule. So rewrite. It has to have the format that it's given. So how can I rewrite this so I can use this one? It has to be c times a function, a constant times a function. How can I rewrite this? Because this way I don't know what to do with it. Anybody? 4 times x? Yeah, okay, so one way we can rewrite it, first, I'm going to rewrite it twice. This is the same thing as 4 times 1 over x squared. That's step number 1. And now we're ready for the second step. I'm still rewriting. I'm not really finding anything. 4 times x to the minus 2. I have to rewrite it as a constant times a function. That's crucial. Now we go to the derivative. What is f prime? Derivative is, that's a constant, it remains, times the derivative of the function itself. So this will give me 4 times. X minus 2, that's my power function. So its derivative is minus 2, that's my n. So from here to here, my n is minus 2 times x to the power minus 2 minus 1. And this would leave me with 4 times minus 2 minus 8 x to the minus 3, which will give me minus 8 over x to the power 3. And that's for that. All right. The last rule we're going to learn today, those are not hard rules really to work with, is the following. I go back to forming functions. So how do we form functions? So we have those basic function x squared, we stretch them. And then to form a new function, we start adding stuff. So I can tell you, okay, for x squared plus 2x, that's a new function. So now the question is, if I know the derivative of that, and I know the derivative of this, how can I find the derivative of this new function that we are building? And the statement is actually, again, not hard. Okay, tells me the following. If I have two functions, f and g, so I have a function f, and I have a function g. So that's my new function here, two functions, and I add them. So I created a new one out of those two. So what's the derivative of this new function? So the derivative with respect to x of this is simply, we can break it up. It's the derivative of the first plus or minus, depending what this is, the derivative of the second. Okay, so if I use the prime notation, so it means the derivative of f plus g is equal to the derivative of f plus the derivative of g. Okay, and we already know the derivative of a lot of functions once we set up this rule. So again, let us do some examples. So example. Okay. Let me take a function, let me call it f because I have to. Let me call f of x to be equal to 4x squared plus, let us say, 6x. As simple as that. So the question is, what is the derivative? So that's the sum, and it's crucial. If we have a sum, then the derivative of the sum is basically the sum of the derivative. It means I can break it up. So we use this verbatim. So what's the derivative of f prime? It's the derivative of this function plus the derivative of this function. I can break it up if I have a sum. Now what's the derivative of 4x squared? So now that's a constant times a function. So that's a 4. Derivative of x squared is a 2. X to the 2 minus 1 plus. Now it's a derivative of 6x. You can do it two ways. Either remember that's a linear. The derivative is the slope. If you don't remember that, okay, I can use the rule. This is x to the power 1. It's going to be 6 times. The rule is 1, x to the 1 minus 1. I hope you never have to use that. I just remember the derivative of 6x is 6. So this will give me 8x plus 6 for the derivative. So we can just do them piece by piece. All right, so let's see one more example along the same line. Let us say I take f of x to be equal. Now let me take a nice piece of paper. Okay. So let me take f of x equal x4 plus 3 over or 8 over x cubed. Okay, and you want to find the derivative. Again, that's a sum. So to be able to find the derivative, I have to do the following. It's the derivative of the first plus the derivative of the second. All right, the first is easy, it's ready. The second is not ready yet. So before I even hit the derivative, I have to make sure I know how to differentiate this term. So I have to rewrite this term to be able to proceed. So I don't start the derivative till I prepare every term. So let us see. This one is x4. This I have to rewrite. So this one to rewrite before I proceed. So let's see what we did. So this is going to be 8 times 1 over x to the power 3. So this will give me f of x. I'm still in the preparation stage. X to the 4 plus 8, 1 over x cubed, x to the minus 3. Okay, now I am ready. Now I'm absolutely ready. What is the derivative? Okay, x4 is simple. It's 4, that's the n, x to the 4 minus 1 plus 8 times. The n is minus 3, x to the minus 3 minus 1. And now we're done. That's 4x cubed minus 24 x to the minus 4. And that's it. That's it. So f prime equal 4x cubed minus 24 over x to the 4. And that's really our answer. So the last 3 minutes, let's take a fairly small example, and just to make it a little bit nicer, just give it some life. So my question is the following. Let f of x be equal to x squared minus 4x plus 2. Okay, simple function. And if we graph this function, if you guys remember, that's a quadratic, that's a simple quadratic. And if we graph it, we have a parabola, this parabola going up. I don't know exactly how it is, something like that. That's the graph. And what I'm interested in is this point, where the lower here. What's this point? What's the coordinate of this point? What's happening here? How can I find this point? Right. Because we always know, like those points, we want to see where the function is bottoming up. So what is the function bottoming up? One way to say it is bottoms up when the slope is actually horizontal. It means it's going to bottom up when the derivative is 0. So my question is, I want to go after this point. So my question is, find the values of x, value of x, where the tangent line, is horizontal. I'm after this point. That's really why we're interested in this. Okay, how we do that? The tangent line is horizontal is when the slope is equal to 0. So tangent and this occur when slope of the tangent line is equal to 0. But what is the slope of the tangent line? The slope of the tangent line is nothing more than the derivative. So it means we have to set the derivative equal to 0 and solve for x. Means we look for the point where my derivative is equal to 0. So what is the derivative? Now we use our rule. F prime is derivative of x squared is 2x minus derivative of 4x is 4 plus 2. 2 is a constant. If a function is a constant, the derivative of a constant, it is 0. That's equal to 0. And now I solve for x. It means 2x minus 4 equal to 0. This means that x equal to x equal to 4. It means x is equal to 2. Okay, so we didn't really do a lot of work, in a way, and we were able to figure out exactly where my function is bottoming up, which is a very important point in a lot of questions. It means, where is my function reaching its minimum value? It's reaching minimum value exactly at x equal to 2. And now if I know the x value, it's easy for me to find the y value. The y value is f of 2. So it means it's 2, and then I have a 4 minus 8. 4 minus 8 give me minus 4 plus 2 minus 2. And I have exactly where my function is reaching its minimum value, exactly where the slope is 0. It means when my derivative is equal to 0. Okay, so with not a lot of work, we were actually able to figure out where my function is bottoming up. All right. Okay, that's it for today. Your homework will be on my lab as usual. Please do them. And I know some know them and a lot don't. So whether you do or not, please make sure you do your homework. All right. And I have office hours, as you guys know, after class. You're more than welcome to come and join. And bye for now. Thanks, Elizabeth.